Hello, I'm Bettina Heinz, Dr. Bettina Heinz, and I will teach you some more about chemistry today. We are discussing matter, which is the basis of chemistry, and we will divide that in two parts. Part one is general ideas about matter. What is it? What are its characteristics? What are its properties? And how does it change? Will they be physical or chemical changes? This is very interesting. So let's look at what we will discuss today, the topics. Matter defined, mass, volume, space, inertia, difference of mass and weight, types of physical states of matter, allotropic forms and modifications, the pure substance, the element or the compound, mixtures, homogeneous or homogeneous, or heterogeneous or heterogeneous, depending on what type of pronunciation you prefer. What is a phase? What is an interphase? And maybe a little bit about radioactive elements and what a natural radioactivity concept implies. So let's start and talk about matter. So matter is anything that has mass, that occupies space, that has a given volume, that shows inertia, that means it wants to resist any kind of change. It can be defined by physical properties as well as chemical properties. Physical properties relate to its shape, form, behavior that does not involve any kind of chemical change. So that means the molecule or the substance or whatever the substance is made up of, the formula remains unchanged. We have here the state, physical state, like gaseous. Is it a gas under normal conditions, a liquid or a solid? Does it have a certain kind of color or sheen, metallic sheen? Internal structure, the type of modification. For instance, diamond, graphite, are of the same element. They're both carbon, made up of carbon atoms, but different allotropic forms or modifications of the element carbon. Then boiling point, melting point, freezing point, or whatever, these are called conversion points. The density or specific gravity, which is related to density. It's density divided by the reference density of water usually. Specific heat capacity, for instance, conductivity, dielectric constant, dipole moment, expansion coefficient, hardness, etc., diffraction index, and so on and so on. So there are many physical constants, many physical descriptions of a chemical. But a chemical property or a chemical change would involve something with which the chemical reacts. That means it converts into a new type of molecular or organizational form that is described by a new formula. So whenever we change the formula of a chemical, then we know that a chemical change has occurred. Now, a property means how does one chemical react with others? Is it flammable? Does it burn easily? Is it combustible? Does it produce heat and light and sound? Is it an explosive chemical? Is it inert, meaning it doesn't react very well? Or is it very highly reactive, etc.? So these are chemical properties, how you relate to other chemicals as a chemical. Now, important is the classification of matter. The first thing that we usually see is whether the substance is a gas, a liquid, or a solid. I'm saying seeing, that means a gas is mostly, in most cases, not visible. If you fly into Los Angeles, maybe you might see a brown layer. That is smog. Those are nitrous gases, nitrogen, oxygen gases that come from pollution, car exhaust, etc., and other things. So these things, of course, they can be visible. But most of the time, gases are invisible. Depends on the concentration, of course. Then we usually can detect whether something is of liquid or solid physical form. So if we look here at the glass, there's some water in here with ice cubes. And of course, what we don't see is the water vapor on top of the surface of the water. So we see here some phases. We see the liquid phase or the liquid state of water, which we indicate by H2O with a little parenthesis subscript L. This tells us that that state is liquid, but the formula, as you see in each case, remains the same. We indicate the ice physical form of water with H2O parentheses S. So that means it's in the solid physical state. The gas or the vapor form of water we indicate with H2O subscript parentheses G. So these are the three major physical states. Now some people might argue, what about plasma? Well, plasma is a physical state that does not involve intact atoms anymore, so therefore it's not of interest to the chemist. Now these three states of matter can be interconverted by removing or adding energy. A liquid can be directly turned into a solid by freezing, by lowering the temperature, or in the reverse, a solid can be changed into a liquid by melting. Then we can also have a connection between solid and vapor or gas. This process is called sublimation. So if a substance sublimes, it goes directly from the solid into the vapor. It can be also considered to be the reverse relationship. When we go from liquid to gas, we are either evaporating, or this evaporation usually occurs when we boil a liquid, but it can evaporate gradually anyway on its own. So a liquid converting into a gas means we are changing the physical state in one direction. We're introducing energy and giving the particles more momentum so that they can go into the other phase. When a gas condenses, we call that condensation. So you see, every phase can be interconverted. Here we see a phase diagram of water, which shows you what physical state it has at different temperatures, which is seen here on the x-axis. The y-axis has the pressure in atmospheres. And here we are where that dotted line is. This is our world. That means water is solid up to 0 degrees. Then we have a range where we are in the liquid phase, in the liquid medium, until we reach a temperature of 100 degrees. Then we go into the vapor phase. Now we live at a range where we have about plus minus 1 atmosphere. However, if we would go to very low pressures, the temperatures change, the conversion temperatures change. Water has a very unusual phase diagram. It has a leftward slant of the solid-liquid interface line, which enables us to ice skate, because when we add pressure with our ice skates onto the ice, it lowers the freezing point at that point. And then we have that slush on which we can glide. Now this has many important implications also for the survival of marine life or let's say aqueous life, water-based life in ponds and lakes, because at high pressure the melting point of the water is much lower. So we can have survival and things are not frozen to death or whatever. Okay, let's move on. Now, I talked a little bit about the movement of particles and the energy content of the various physical states. In the gaseous physical state, we have the most kinetic energy involved of the particles. So we have very mobile, very flexible, very free particles, and these do not cohere in any fashion. So they're very independent little creatures, so to speak. In the liquid, we are confined by whatever container we have. We have an interface, that means a surface between liquid and the environment or its own vapor. And these particles now are relatively free to move around, but they are not quite as free as in the gaseous phase. It's almost like a crowd in the street or in a football field leaving the premises, trying to get out of the gates. So people are moving in a certain direction, but they cannot move as they want to. But they're not stuck like in the seating arrangement. So they're liquid, in a liquid state. In the solid state, everybody is situated in one position. You're stuck in that position. You can move around a little bit, wriggle and raggle, scratch your head or so, but the particles are confined in their lattice points. That means if they are in a crystal organizational process, they are pretty much stuck in their position. But they have a freedom of movement, but not much. We differentiate between crystalline solids and amorphous solids. Crystalline means an internal order of the building blocks or the particles that make the crystal. We have different types of crystals, like metallic, ionic, molecular, etc. And then amorphous means no internal structure, but still is solid. Now one might consider this a borderline case because glass, and here I have some glass tubing that I'll put on here. This is glass. Glass looks pretty solid to me, but actually internally it is what we call a supercooled liquid. That means the long molecules that are made up of these minerals, like aluminum oxide, potassium oxide, sodium oxide, sort of act like snakes in a frozen animation process. They don't move around much. So you have a solid appearance, but internally it resembles more liquid. Another borderline case are the liquid crystals, where the molecules behave like fish schools. They move around from A to B. Translational movement is possible, but they're very organized. It's like an organized liquid. And here we see that enlarged. Now, what holds these particles together? They're usually intermolecular forces. We have a different range of intermolecular forces, but we won't go into that right now. But I will show you here the difference of the free-moving molecules, like here with the water molecules. When all the intermolecular forces, the dipole forces are intact, we have a nice regular arrangement of the water molecules, a hexagonal arrangement. And that's why actually ice is less dense than the liquid, and we have ice cubes floating on top of or at the interface of the liquid and the vapor above. Now, another borderline case I just mentioned was the liquid crystal. Liquid crystals are found in insects, especially in beetles. They have these beautiful light patterns. And there's a very intricate change in the organization going on that we don't want to go into. Another interesting natural phenomenon of liquid crystals are found in the bilayer membrane of the cells, and there's certain diseases that have to do with different liquid crystal arrangement patterns that can be a problem for the individual. Here we have an amino acid missing. There was in sickle cell anemia, for instance, glutamic acid is replaced by a very nonpolar amino acid, which is valine. So we have to add this valine in this little segment there. Now, we have matter all around us. Everywhere we look, we see material around us. And most of the material is tangible. We can touch it, we can see it, we can look at it and see differentiate between different materials. For instance, here I have a wonderful alum block, crystal block. It's not a monocrystal, but it's definitely a solid, as you can see, partially crystallized. It's used as a deodorant, and it can also purify water. It has many good applications. And here we see how the physical properties differ from the chemical properties. We've mentioned already that the physical properties are usually determined by physical constants, and the chemical properties are usually determined, or we should rather say, they are determined by the reactivity of the chemical, how it behaves with other chemicals. Now, properties we can distinguish. Metallic sheen, for instance, like here in my spatula, is a result of a physical property, the internal organization of the building blocks within the lattice, the crystal lattice. But what if I would burn this spatula or treat it with a lot of heat, and will it oxidize? That would be a chemical change. However, this is a non-magnetic steel, so that's not going to be very reactive. But we will show in a little video how one metal is very reactive, and that is magnesium. So magnesium can burn easily if we activate it a little bit, and it will combine with oxygen to produce an oxide. That would be a chemical change. Let us see this video right now. Hello. Today we will demonstrate a combustion process right in front of your eyes. We will have some magnesium ribbon here that comes off the roll. Can break off easily. I made a little strip here. I have to polish it a little bit because magnesium is a reactive metal and easily already reacts with oxygen of the environment and makes a little passivation of the metal, meaning a small magnesium oxide film, and we have to rub this off so it can react very well with the flame. The flame is actually the activation energy needed for the metal magnesium atoms to react with the oxygen of the environment. So we have to activate that process. It does it in the cold already, but the heat will accelerate the process. And it's an exothermic reaction, so it demonstrates this type of reaction as well. The only thing is we get a bright flash of light. So be careful when you look into this flame that is produced. Magnesium used to be used in the old flash bulbs. See, it's happening pretty fast. Here we go. It burns. And I'm going to pour it then into some water. See, like a beautiful little ash thread. I let it dab on here. You see some residue, which looks like a pigeon flew over here, but that's not the case. This is the white powdery substance is magnesium oxide now, but a little contaminated with magnesium nitride. So this powdery substance now, the white powdery substance, will eventually dissolve in the water and make a base, which we call magnesium hydroxide, which would give a basic reaction with universal indicator paper. It might be too early to see any results right now, but if we wait long enough, this paper would turn blue or green. Right now, it's still neutral. That means it takes a little time for the magnesium hydroxide to dissolve. If we move to this Bunsen burner now, we can see an interesting chemical device which we call the crucible. The crucible is a porcelain container. That means it can withstand a lot of heat, made out of bone china with a lid. Remember, you cannot touch this with your bare hands. You would receive terrible burns, so we use the crucible tongs to work with hot materials. You see here a tripod of iron and a clay triangle, which is used to nestle the crucible. And in a chemistry lab experiment setup, we use magnesium coiled ribbon to put into the crucible, and then let what I did here in a fast process, let this happen gradually in an experiment which we will call the determination of the empirical formula. Empirical means by experimentation, of magnesium oxide. What is the actual formula? So what we do, we weigh out the magnesium ribbon carefully on the scale, note down the mass, then we let it react with the oxygen. Of course, we have to leave the whole thing a little bit open so it can have contact with the air. And then the magnesium will gradually react with the oxygen. I can sort of tell when the ribbon becomes sort of red hot, then there's something going on. The magnesium will also react with the nitrogen. So we get two compounds. We can squirt a little water in here to dissolve the magnesium nitrate. It will decompose into magnesium oxide and ammonia. So it will leave the territory easily. So in the end, we only have magnesium oxide. Once the process is finished, I can weigh the magnesium oxide after cooling, of course, and then the original magnesium mass I have the product mass, subtract both from each other, and then I have the oxygen amount, and then I do some mathematics, and I can get the percentage composition and eventually the actual formula of magnesium oxide. And I can tell you it will be MgO, whereas magnesium nitrate would be Mg2N3. So I hope you enjoyed this little demonstration. Until next time. Here we are back again, and I hope you enjoyed that little video. We would like to look here at the candle now and see what is involved in this whole process. Now we know what a physical and a chemical change is now, but do we always recognize it? So here we have a candle burning. The wax is melting, so the wax is just changing its physical state. That would be a physical change. The ignition of the wick, which is cellulose of the candle, that is a chemical change because it reacts with the oxygen to produce a variety of oxides and energy and light. So that is what we call a combustion. With the air, the oxygen is also being changed chemically because it combines with the cellulose to make new products. The activation energy is needed to get the materials reacting. So you see chemical changes depend on environmental conditions. So we usually heat and activate in order to get the reactivity that chemicals have in operation. Now, very reactive chemical, we usually keep in a refrigerator or in cool spaces so that they won't react too fast for us, so that we can preserve it a little bit longer. A similar physical change that we could have observed in the lab, just like the magnesium burning, is heating a copper wire. And the copper wire will then turn into a red hot material and will, under certain circumstances, if we have enough activation energy, then the copper can combine with the oxygen to make a dark black powder on its surface, which, if we analyze it further, happens to be copper 2 oxide or cupric oxide. If we really monitor this reaction and weigh out the copper wire and measure it after the blackening effect, then we notice that the mass has increased by 0.25 grams in this example. So that means the oxygen that reacted was 0.25 grams. So with this, we can establish the empirical formula or the actual formula of the product. So in a way, we have two things happening here. We have a physical change. That means when something is red hot and glowing, the particles are just moving around faster. It's not changing yet. But when the reaction occurs and we have a new chemical involved, then that is a chemical change. Here we have a very unusual liquid, the superfluid helium. Now, helium is normally a gas, but under certain PT conditions, pressure temperature conditions, it has a certain modification or allotropic form where it seems to defy gravity and creeps up a test tube on its own or would come out of a coffee cup on its own. So that's an interesting little phenomenon. So under different environmental conditions, things can change in a very strange way. Now, one more thing that we want to show here is radioactivity. Radioactive chemicals can also convert into something different. This is, of course, due to a nuclear change. That means the electrons are not involved of the electron shell, but the nucleus is somehow unstable and will give off certain radiation forms like alpha, gamma, and beta radiation. Now we have either alpha emitters, that means they only give off alpha particle rays, plus gamma rays, or we have only beta emitters that only give off electrons as particle radiation, which we call beta, but in each case we have gamma as an accompanying energy radiation. The penetration is different because helium particles or helium nuclei, the alpha particles are much heavier, so they cannot penetrate as far as, for instance, the beta particles, which can be held back by aluminum foil. And gamma radiation is very penetrating and can only be held back by lead. So that is a change which leads to a new form of element. And let me just show you this again. The element will be changed in atomic number as well as mass number when we have alpha, but going in a different direction than when we have beta decay. With this, I'd like to say goodbye to you.